Welcome. Our next lecture is on sequence. Okay. Coming from our previous lecture on proof by induction. Next, we want to look at sequence. What is a sequence? A sequence is a set of numbers. These numbers, generally, we can denote these numbers by U1, U2, U3. And these numbers, they are in a defined order, or they are folding according to a rule, a definite rule that we are using to get these numbers. For example, we can have numbers like 2, 4, 6, 8, 10. It's a sequence going upwards. And we can have numbers like 1, 2, 3, 4. It's a sequence. 3, 6, 9. It's a sequence. But there are different rules that we use to come up with these terms in a sequence. Okay. So, but you need to know this terminology. Each number in a sequence is called a term. So if you just look at maybe, for example, U4 in this sequence is a term, U3 is a term, U7 is a term, okay? And then the nth term, UN, the nth term of a sequence is denoted by UN. UN is a general formula that we use. UN just means the nth term, meaning any number. It can be, so we use UN to come up with any term in our sequence, to come up with any term that we want in our sequence. Like, for example, if you want 1, we can just say U1. If you want 2, U2, U3. So UN generally is a formula that we use to come up with other terms of our sequence. And it's called the nth term. So the nth term in a sequence is very important because it gives us a formula that we use to come up with any term in our sequence. Okay. It's usually written as UN, or we can just write it as UN or UN. So, for example, we can have a sequence like UN is equal to 2n. Can you write terms of that sequence? Okay. So U1, we put 1 there to get U1, which is 2. We put 2 there to get U2, which is 4. 3 there to get U3, which is 6. So that's the sequence 2, 4, 6, 8, 10, 12. And that's the sequence that. So, for example, that's the sequence. So this sequence is called. So each sequence can be a finite sequence or an infinite sequence. If it's a finite sequence, it means there is an ending point in the sequence. It doesn't necessarily mean that this sequence they continue going upward. Some sequence can end for n up to 10, for n up to 20, somewhere along the way it ends. Then when it ends, it's called a finite sequence. When it does not end and the terms continues going upwards up to infinite, it's called an infinite sequence, according whether there is no a finite number or a finite. Some sequence that you're going to sometimes this sequence the sequence can be given in form of a formula, like this simple formula that we have seen here, or it can be any formula, like, for example, this sequence here. It's a sequence again. And when it's given in form of a formula that you have got any only in it, then the sequence is said to be given as a recursion formula. It's given as a formula. Okay, just as a formula. But sometimes a sequence is when the sequence is given in a formula like this, it's just a formula that we use to calculate UN. But sometimes we are able to write the sequence using a formula such that inside the formula here, there are terms or previous terms of our sequence. Like, for us to get UN, inside this formula, there is UN minus 1, or there is UN minus 2. Then when it's like this, like when it's like that, the sequence is said to be given in the form of a recursive formula or a recurrence relationship. So far, UN may be defined by a formula like UA in terms of, for example, like this. This is not a recurrence, but we cannot. We can also define a sequence by giving a relationship or a formula that connects successive terms of our sequence and specify values of the first or the second. So when it's given like that, it's another way of giving you a formula of a sequence. When it's given like that, we say it is given in form of a recurrence or Kazan formula. It can be given as a formula like this. Formula is similar to just this formula that we have. It's not a recurrence formula. But when it's given like this one, the next example, we call it a recurrence formula. A recurrence formula is like this one. You see now, here, our un plus 1 is found by using un. Therefore, it is a recurrence. Okay, it's not only found by n. So if the formula you have got n only, it's just a sequence with a formula. But when our un or un plus 1 is found by somewhere in the formula, there is un minus 1, un plus 1, so there is a term with un, remember, it's referring to another term in the sequence. Then it is said a recurrence formula. How do we come up with the terms in a recurrence formula? A simple example is this one, whereby we are saying un plus 1 is equal to 2 over un, and you are given u naught. Okay, so for us to get u1, where there is n put 1, we can see that u naught is equal to u naught, u1 is equal to u1 is equal to u naught plus 1, which is u1, 2 over u naught. And what is u naught is 1. So u1 is equal to u naught plus 1. And what is u1 using this formula is 2 over u naught. And our u2 over u naught, our u naught is given here as 1, which is equal to 2. Then when you want to now to get u2, you use u2. For you to get u2, you need u1. For you to get u1, you need u naught. That's why u naught you are given. And then for us to calculate this u1, we have used u naught. So for us to calculate u2, we need u1. And how do you calculate u2? u2, we use this formula. un plus 1 is equal to 2 over u1, which is 2 over u1. And u1 is there as 2. So it's 2 over 2, which is equal to 1. For us to calculate u3, we need u2. And how do you calculate u3? u3 is 2 over u2, it's 2 over u2, which is 2 over u2. And what is u2? u2 is 1, so it's 2 over 1. Then the terms continue. So when it's like this, it's called a recursion or a recurrence formula. We're using previous terms of our sequence to calculate the next term of our sequence. It does not necessarily mean that we only have to use the previous term only. Some recurrence, some recursion formulas are so complicated that sometimes we need to use the previous and the previous, or the last 4 terms, the last 5 terms, something like that. Like this is a good example. un, in this case, we are not using u, we're using a in our sequence. And we know that u naught and u1 is equal to 1. And the formula that we are given, the recurrence formula, is un is equal to un minus 1 plus 2 un minus 2. So it means we are using the previous 2 terms to calculate the current term. Can you calculate? And here we are saying for n being greater than or equal to 2, because u naught is given as 1, u1, sorry, not u, a1, a naught is given as 1, a1 is given as 1. So can you calculate a2? a2 is equal to a1, so a2 is equal to a1 plus 2a naught. And what is a1? a1 is 1 plus 2 times 1 again, which is equal to 3. So a2 is equal to 3. a3 is equal to a2 plus 2a1. a4 is equal to a3 plus a2. a10 is equal to a7. a10 is equal to a9 plus 2a8. But for you to get a8, you need a7 and a6. For you to get a6, you need a5 and a4. So you cannot calculate a20 from Norway. You have to first, for you to get a20, you need a19 and a17. For you to get a19, you need a18 and a17. So you cannot just come from Norway and calculate a20. You need to calculate all the previous term of that sequence up to a certain value. And when it's like this, it's called a recurrence or a recursion formula. So the question here is find a6. Unlike when the sequence is given as a formula, when it's given as a formula like this, we are able to calculate any term that you want. If I want a 100, when there's n, I'm just putting 100. If I want u100 is equal to 2 times 100 squared minus 500 plus 4 over square root of 100 squared plus 2. That's a formula. But when it's given as a recurrence formula or a recurrence formula, you need previous terms which are there in the formula for you to calculate the next terms. But one thing about these sequences is that we should be able to calculate the limit of a sequence. Okay, what is the limit of a sequence? Let's now consider un equal to 1 over n, a simple sequence like this. This sequence can be easily written, un is equal to 1 over n, can be easily written by as this, because the sequence is when n is 1, that's 1, when n is 2, 1 over 2, when n is 3, 1 over 3, when n is 4, 1 over 4. So it can be written as 1 half, 1/3, 1 over 4, 1 over 5, 1 over 6. You can see now that this sequence, as the sequence of the term goes to infinity, or as n approaches infinity, the terms are slowly becoming zero, are slowly tending to zero. But this sequence does not end because it has got these 3 dots, which means it goes up to infinity. So somewhere along the sequence, we've got 1 over 1 billion. And what is 1 over 1 billion? Is 0.0000000. And we've got 1 over 1 zillion, which is 0.00. So as the sequence, as we write the sequence, these numbers are approaching a zero. And when a sequence is such that it's approaching a certain number, the terms are tending to are becoming a certain number, we say that the sequence is approaching a limit. And in this case, in this specific example, the terms are tending or approaching a limit of zero. Okay, so the limit of a sequence differs from sequence to sequence, and some sequences don't approach a limit, some approach a limit which is not zero, some approach 0, some approach 20, some approach 100, depending on the sequence. Okay, so are we now able to define what is a limit of a sequence and being able to find these limits? Okay, so a limit of a sequence L is called the limit of an infinite sequence. So this sequence have to be an infinite sequence. So a limit L is called a limit of a sequence, of an infinite sequence, A1, A2, A3, A4, which means the terms continue up to infinite. But as they go up to infinite, which number are these terms approaching? Or generally, we can just call this AN. If for any positive number, epsilon, we can find a positive number n, which depends on epsilon, such that the modulus of an minus L is less than epsilon for all integers of n greater than n. And we write this mathematically as limit as n approaches infinity of an is equal to L. What we are simply saying is, if a sequence is approaching a limit, then there is a number n such that if you subtract the nth term of your sequence with your limit that limit is approaching, you get a very small number which is less than epsilon. Okay, like if you are saying there is a limit and there is the nth term of our sequence. So if a sequence is approaching a limit, it means that the nth term of our sequence is slowly becoming L, and the difference between L and the nth term is slowly becoming smaller and smaller, and becoming a small number, epsilon. So if a sequence is such that an minus epsilon, the modulus of that, we just say the modulus of that because we don't know whether it's going to be positive or negative. So the modulus of an minus epsilon minus L. So L is our limit, and an is our nth term. So if a sequence is approaching a limit, okay, 1 over 1 billion is not zero. Consider this sequence which we have above here, which is approaching 0. 1 over 1 billion is not 0. But the difference between 1 over 1 billion is the 1 billion term of this sequence. So, but 1 over 1 billion is almost similar to 0. But the difference between 1 over 1 billion and 0 is less than epsilon, a certain number which depends on n. And for a certain number n, which is greater than n, this is always true for n greater than n. Okay, this is logic. You need to be very, very careful when you're defining the limit of a sequence. Okay, Since this is online, I'm not going to waste much time. What we are simply saying, these are the diagrammatic representation of the definition of a limit of a sequence. So what is this? If a sequence, these are the terms of our sequence: 1, 2, 3, 4, 5, as we go, and it. Then there is a limit L which this sequence is approaching. So if it's approaching a certain limit, the terms of this sequence will get closer and closer to a certain line, which is L here. But it will never touch the sequence, the line, but it will get closer and closer. So if a sequence is approaching a limit, the difference between a limit and epsilon, whether we're saying L minus E or L plus E, will be less than E. Okay, or the difference between the nth term between an. So there is a number n somewhere in our sequence such that these dots are representing an. Are we together? So this dot here where my cursor is minus L, somewhere here, this distance is bigger than E. You can see that this distance is bigger than E, okay? Then let's go to n equal to 2. This distance here is still bigger than E. Are we together? Then let's go to n equal to 3. This distance here is still bigger than E. Then let's go to n equal to 4. This distance here is bigger than E. But there exists an n which is greater than n. Our n here is now here, such that pachazosvika pekuti our an minus L is all less than epsilon for n greater than n. Saka tichibva pana n uyu ari pane kesa yangu apa, tichienda kumusoro kwesuku up to infinity, wana an wedu apa pane madots minus L are all less than epsilon, because epsilon is this distance from our limit L up to here, from our limit L kusvika pane line rine madots, and the plus L plus epsilon is from this line kusvika pane line rine madots. So if a sequence is approaching a limit, there exists an epsilon such that a n minus L is always less than epsilon for n greater than n. So to no, okay, a n minus L hatange hake ari less than epsilon, a n minus L, but paripo there exists an n which is greater than a capital letter N, such that a n minus L is always less than epsilon. Saka tazosvika somewhere panapa pekuti tichibva panapa tichienda kumusoro kweso, for all n greater than n, a n is always, a n minus L is always less than epsilon. Samukona kubva panapa a n wedu ndeapa pane dot minus L which is less than epsilon. Epsilon kubva pane line kusvika apa kana kuti kubva pane line kusvika apa, handiti? Saka a n uyu minus L is less than epsilon, a n uyu minus L is less than epsilon, a n uyu minus L is less than. Saka tikuti for all n greater than n, an minus L is less than epsilon. Saka zvoti tichibva apa pana n apa, going upwards, an minus L is always less than epsilon. So this is the case whereby the limit is, whereby our an is approaching the limit from below. It's also true when the limit is being approached from above. Somewhere there exists an n such that an minus L is always less than epsilon. So from here, this n indicated here, this n which I have highlighted here, going upwards, an is now, an minus L is now less than epsilon. Okay. So this is also true. The definition is also true when the limit is being approached. This is from when the limit is approached above, the example that I explained, and when it's being approached from below. Some sequences approach a limit, what do you call, from in a random way. Okay. So when it's somewhere here, when n is 1, is above, the limit is below, it's above, it's below, it's above, it's below. But generally, as n approaches infinity, the sequence is approaching a certain limit L. Still, if you subtract an madots, L in the uyu, an minus L upper is bigger than epsilon, upper is bigger than epsilon, upper is bigger than epsilon, upper is bigger than. But somewhere there exists an n along the way in our sequence. In our sequence, such that an minus L is now less than epsilon for all n greater than n. Tichibva pana n apa tichienda uku, the difference between an and L is now less than epsilon. Sometimes even if we talk of a limit as a constant, here it's just a constant, the definition still holds. Okay, so this is the definition of a limit. Please understand that definition because it's very useful. We are going to make use of that definition in proving some other mathematical terms that you are going to prove. Then we have got this sequence 3 plus 1 over n, which can also be this 3 plus 1 over n, which can also be written as 3n plus 1 over n by just adding these terms. You can see that the sequence is 4, 7 over 2, 3 over 10, and so on going upwards. So we can show that, the limit of this sequence as n approaches infinity, the limit of un is equal to 3. Okay, we want to show that. So when we are showing that the limit is equal to a certain number, generally if the limit exists, the limit also converges. The sequence is also said to be convergent. So if a sequence is approaching a limit, we say the sequence is converging. Otherwise, if it's not approaching a limit, not all sequences approach a limit. 2, 4, 6, 8, 10 does not approach a limit. Okay, so when it's not approaching a limit, it's said that sequence is said to be diverging, or it's said to be divergent. When it's approaching a limit, then it's converging. Okay, so to find a limit, usually we use this. This is our basic sequence. We know that the limit as n approaches infinity of 1 over n, that sequence that we started with is equal to 0. So we usually use this result to find the limit of other sequences. I'll show you how to do that. So if you want to show that this sequence, this is equal to 0, we say let epsilon be a number greater than 0. We can find any e which depends on e, such that you can see this is the definition of the limit that I explained above. This is our an. An when we do the 1 over n minus L, which is this one. Okay. Then which we can simply, so that's an minus L, modulus of an minus L, which we have here. Then if we simplify modulus of 1 over n minus 0, it's just modulus of 1 over n. Okay, so this should be, and since n is positive, we know that n is an element of integers, because n is equal to 1, 2, 3. And we know that the modulus of 1 over n is just 1 over n. And this should be less than epsilon. Okay, from the definition of the limit, because we are saying an minus L should be less than epsilon. So this is our an minus L, which we have simplified. In this example, our L is 0, so minus 0, we just have 1 over n, and the modulus of the positive number is always that positive number. This should be equal to 0. Now what you do if you want to show that the limit is equal to a certain number, you then, when you come to this inequality, you then make your n subject. So if I multiply by n both sides, remember m is positive, n is positive, e is positive. Multiply by n both sides and divide by e. I'll get n is greater than 1 over e. Okay. Then when I come to this stage, I then change this n. Since I'm saying there exists an n which is greater than n, for somewhere along the sequence there is an n, there exists an n which is greater than n. So pandoya ndati n panapa ndobva ndachinja n mudiki uyu, then I say n muhombe is equal to, ndachinja, then I then change the inequality sign into an equal sign, then change the small letter n into a capital letter n, then I then say n is equal to 1 over epsilon. Then I find the limit of epsilon. Here you can see that when n is equal to 1 over epsilon, what is the epsilon? As n approaches infinity, so as epsilon, you find the n as epsilon approaches 0, because we want epsilon to be as small as possible. Okay, as epsilon approaches 0, as this approaches 0, n approaches 0. This capital letter n will be equal to 0. Therefore, we can see that the limit of this sequence is equal to 0, because as epsilon approaches 0, this capital letter n approaches 0. Now taking n to be a smallest, so we take n to be the smallest integer greater than 1 over epsilon, taking n to be this first integer greater than 1 over epsilon. Okay, so which means as epsilon approaches 0, n will also approach 0. Therefore, the limit of 1 over n is equal to 0. That's how we prove this limit. I hope you are able to follow. Can you prove also that the limit of 1 over n to the power p is equal to 0 for p being element of natural numbers? Use the definition of a limit to prove that this is equal to this one. So I will go through this one. See, and then you will try to figure out how to do this one. You try on your own. We are using the same method as the method that I explained above. Okay, so what is the definition of the limit? An minus L should be less than epsilon. Modulus of an minus L should be, this is our an ndiye uyu. Mandati highlighter uyu. Saka ndinonyora panapa an minus L ndo limit yedu, which is 2 over 3. So an minus L ndiye uyu. This is our an, that's the modulus of an minus L. And we are saying this modulus of an minus L should be less than epsilon. Then let's simplify this. So when you are now proving that the limit of this is 2 over 3, you write an minus L modulus of an and simplify it. That's the first thing. And let's simplify it. If we simplify this thing, you see that this is a fraction that we are just combining. That's 3n plus 2. If we combine it, we get that. Then we add the two fractions and simplify to that. Then we've got 6n minus 6n, which simplifies, and then minus 3 minus 7, that's minus 3 minus 4, that's minus 7. So if we simplify that, we get a minus 7 over this one. Okay, that's the simplification of that. And what is the modulus? So what is the modulus of this? The modulus of minus 7. Since n, remember, n is always a positive integer. Where n is a positive integer, it's stated here. For n being a positive integer. So what is the modulus of this denominator? This denominator is always positive. Because n into 1, 2, 3, 4, n is a counting number. So it's always positive. The numerator is very negative. So what is the modulus of this? So the modulus of this no be some minus. And then we are left with 7 over this. Here we're supposed to write this without the modulus. Okay. So we're saying the modulus of an minus L should be less than epsilon. And what is the modulus of this thing? The modulus of this thing is 7. Tapata bizama modulus because pamsoro minus 7 means a positive. And the denominator is always positive. So we're saying 7 over 3n plus 2 should be always epsilon. So what should happen now? You then make your n subject of the inequality. So here, tina epsilon at kunoko, na n at kala. What do? You just multiply by 3, multiply by 3 here. Kuna 3 epsilon divided by 7 divided by 7. 3 epsilon over 7. Then tina 1 over this. Then 2 invert both sides. So tina 3n plus 2 over 1 being equal to 1 over 3 epsilon, not being less than 1 over 3 epsilon, 3 epsilon over 7, something like that. Then to Tasani each the soro I was going to work out this one if I had a whiteboard here, but I never whiteboard. But I'm sure you can clearly see that takasana 3n plus 2 akazoya u that divided by 3. We will see that n is greater than. Remember, we need to reverse the inequality sign. After multiplying by, when do we reverse the inequality sign? After inverting both sides. When you invert both sides, you reverse the inequality sign. That's why we now have n is greater than 7 minus epsilon over 9 epsilon. Okay, right. Then the moment you acknowledge Kapanab, you then change this small letter n into a capital letter N and put an equal sign. Okay, like here. Then you take n, so n is equal to this. That's what you just did here. So take n to be equal to this. Then take n to be the smallest integer greater than this thing, which means you are simplifying this limit as epsilon approaches 0. As epsilon approaches 0. So how do we simplify the limit? This limit is epsilon approaches 0, because we want epsilon to be as small as possible. Divide each of these by epsilon. So if we're 7 over epsilon, 6 epsilon over epsilon, 9 epsilon over epsilon. So epsilon over 6 here cancels out, and here cancels out. So now 7 over epsilon. As epsilon approaches 0, 7 over epsilon approaches 0. So we are left with 6. And this one approaches 6, and this one approaches 9. So that's 6 over 9, which simplifies to, and we want the modulus of that, the positive integer, the smallest integer. So which means the limit of this becomes 6 over 9, which is 2 over 3. Okay, so we have got this thing, divided by epsilon, divided by epsilon, divided by epsilon. So one epsilon, I want to cancel now, which is 6 over 9. So the simplified minus disappears because we're looking for the positive integer. So which means 6 over 9, that's 2 over 3. So the limit of this is 2 over 3. So you have proved that the limit of that sequence is 2 over 3 using the definition of a limit. Okay. Then we need to explain or to understand the theorems on limits. When we're evaluating limits, if the limit of a certain sequence an is equal to a, and the limit of another sequence bn is equal to b, then the limit of an plus bn is equal to the limit of an plus bn, which is equal to a plus b. This just means, okay, let me just explain that at the end. Then the limit of an minus bn is equal to the limit of an minus the limit of bn, which is equal to a minus b. The limit of an times bn is equal to the limit of an times the limit of bn, which is a times b. The limit of an over bn is equal to the limit of an over bn, which is a over b, provided that the limit of bn is not equal to 0, because we cannot divide a number by 0. So if the limit of bn is equal to 0, then we have a problem to find another way of simplifying that limit. So what we are simply saying here is my limits ema-terms ano-edana kana ano-subtractana, ano-multiplyana, ano-dividana kana limit yedenominator isiri 0 anongowanikwa nekutsvaga ma-limit of each of that term in the sum difference product or division. Indeed. So which means using this theorem, we are able to find limits of a sum of some limits, of the sum of some limits. Okay. Then another theorem again is the uniqueness theorem. The limit of a convergent sequence un is a real number and is unique. We cannot find the limit of a sequence un which converges to be two different numbers. Okay, so it's always unique. There's always a single limit when the sequence converges. When the sequence converges, there's always a unique limit. So that's the uniqueness theorem. A convergence theorem, a convergence sequence always has a unique limit. To prove that, okay, let's prove that a convergence sequence has got a unique theorem. We want to show that if the limit of a certain sequence un is L1, and let's assume that it's not unique. If it's not unique, it means there are more than two limits. Then the same sequence un, as n approaches infinity, the same sequence is also approaching another limit, which is L2. Okay. Then we want to prove that if that's the case, then L1 should be equal to L2 by the hypothesis, which shows that it is unique, the limit is unique. Then if we are not able to show that L1 is equal to L2, then we show that it is not unique. But in this case, since our sequence is the same un, and as n approaches infinity, the sequence of this, the limit of this sequence should be unique, which means L1 should be equal to L2. Then, by definition of a limit, we know that there exists an epsilon which is greater than 0. We can find an n such that using the definition of a limit, the definition of a limit is very important in this module. We want to show that un minus L1, the limit, is less than epsilon over 2, which means that since our epsilon now is since we are proposing that the limits are 2, which means the epsilon now is being split into 2, that's why we are dividing by 2, but still epsilon is a positive number, so we can just say it's equal to epsilon over 2 for n greater than n. And also using another possible L2 limit L2, we are saying the modulus of un minus L is less than epsilon over 2. So this is the definition of a limit. But here we're using the other limit, here we're using the other limit. So for n equal to that. So we know that L1 minus L2 is equal to L1 minus L2 is, because AN is the same sequence, which is the same sequence which you want to prove. So the modulus of L1 minus L2 should be equal to the modulus of L1 minus AN plus AN minus AN. Since I am subtracting AN and adding AN, it means this is equivalent to L1 minus L2, because I just added AN and subtracted AN. Okay, then we know that this is always less than L1 minus AN plus AN minus AN. So I'm now splitting this into two. L1 minus AN plus, using the triangular inequality, we know that this thing is always less than L1 minus AN plus AN minus minus LN. And what is this? This is less than, by definition of a limit, L1 minus AN that we have mentioned here. We know that this thing, the first sum here, is less than epsilon over 2. And this is also less than epsilon over 2. So the sum of this is always less than epsilon over 2 plus epsilon, which is equal to epsilon. Therefore, L1 minus L2 is less than any positive epsilon. However, epsilon is small, and epsilon must be 0, because we want to make epsilon as small as possible. So which means the modulus of L1 minus L2 should be equal to 0. Okay, so if L1 minus L2 is equal to 0, this shows that L1 is equal to L2, which shows that these limits L1 and L2 are unique and they are equal. Okay, that's how we show the uniqueness theorem. That's how we prove the uniqueness of a limit of a sequence. Also, we want to prove that we, following the same argument that I have explained, that if the limit of AN is equals to A and the limit of BN is equals to L, prove that the limit of AN plus BN is equals to A plus B. Still, we need to use the definition of a limit. By definition of a limit, we know that the modulus of, using this, what you want to prove, the modulus of AN plus BN minus A plus B, because the limits of this A plus B should be less than epsilon. Then we come here, the modulus of AN plus BN minus A plus B should be equal to the modulus of AN, because we are now using the properties of modulus, AN minus A plus BN minus B. It's just a matter of separating these things. AN plus A plus BN minus B. And what is this one? This should be less than, using the properties of modulus, this should be less than the modulus of AN minus A plus the modulus of BN minus B. And what is this? This is the limit of AN, and this is the limit of BN. Therefore, given any epsilon greater than 0, we find N1 and N2 such that AN minus A is less than epsilon over 2, and BN for n greater than N1, and Bn minus B, and Bn minus B is less than epsilon over 2 for n greater than Bn. So which means that the modulus of An plus Bn plus A plus B should be less than epsilon over 2 plus epsilon, which is epsilon. Therefore, it means we now have two integers, N1 plus N2. And the n that we want for n greater than n is the maximum of N1 plus N2. Hence, the limit of An plus Bn is equal to A plus B. That's a way of proving that the sum of two sequences is just equal to the sum of, to the individual sum of that sequence. Then sequence tending to infinity. Some sequences are like what I explained before. Some sequences are finite, some sequences are infinite. As n tends to infinity, n, that is, we write it as n approaches infinity, like that. Which means as n grows beyond bounds, that's infinity. Infinity is not a number. It's just infinity is not a number. Okay. So we write that the limit of an as n approaches infinity is equal to infinity. Is equal to infinity. If for a positive number m, we can find a positive number n depending on m, such that an is greater than m for n, or n greater than n. So this sequence here is not approaching any limit, so it's diverging. If a limit is diverging, tukuti isusu pana an which is greater than m, tukuti my terms they are growing bigger and bigger, and which means an is always greater than m, which means if the limit of an is equal to infinity, we are saying the terms of our sequence an are always becoming bigger and bigger and bigger and bigger as n up. Otherwise, the terms are increasing. So that's why we are saying an is always greater than a certain number m for n greater than n. So we are saying an will be becoming bigger and bigger and bigger. Okay, as n approaches infinity. Similarly, if the limit of a sequence an is approaching a negative infinity, which means it's going to the negative infinity, to the negative side of the real number, then if that sequence is approaching a negative infinity, we are saying we can find a positive number m such that an is always less than m for n greater than n. To put it as n goes, my terms they are becoming smaller and smaller and smaller and smaller. A10, A11. To compare A10 and A11. Can I treat a limit of n as n approaches infinity of an is infinity? A10 na A11. A10 anenge ari mudiki pana A11. A11 anenge ari mudiki pana A12. A12 anenge ari mudiki pana A13. A13. So we are saying that an is always greater than m, a certain number. Okay. The same thing, if you are saying the limit of an is equal to minus infinity, to put it, A10 is less than A11. A11 is less than A12, which means these terms are becoming smaller and smaller. Okay, prove that this thing is the limit of this is equal to minus infinity, the limit of this equals to infinity, the limit of this equals to minus infinity. We can as well prove that. When we are proving that, you see that the limit, you are just using the definition of a limit to show that as the n approaches infinity, then the limit of that epsilon of that capital letter N is infinity. For each positive number m, we can find a positive number n such that a n is greater than m and a for all n greater than n. Then we are saying 3n to the power 2n minus 1 is greater than m, which is our sequence. They say it's greater than m. So if it's greater than m, it means we are saying this is an index, which means we can apply the laws of index, which is 2n minus 1 ln 3 should be greater than ln m by taking ln both sides. And then we divide both sides by ln 3 to make, we are now trying to make n subject of formula. Divide both sides by ln 3 plus 1 both sides, divided by 2. When we are dividing by 2, we just multiply by half. So n should be greater than half open bracket ln m plus ln 3 plus 1. By taking n to be the smallest integer such that this one, you can see that when you come to this one now, you can say that by taking n to the smallest integer, what is this one as n approaches, as m approaches 0? As this m approaches 0, this thing here, as m approaches 0, this thing here approaches infinity, because 0 m, as m approaches 0, ln m approaches 0. Then 0 over ln 3 is an infinite, plus this one that's an infinite, so this one approaches infinite. Therefore, the sequence approaches infinite. Using the same argument, you can also as well explain the previous, the other example. Bounded in monotonic sequence. A sequence is if a sequence tends to a limit L is said to be convergent. I have explained that. A sequence which converges to L, then a sequence A which tends to a positive infinity or negative is said to be divergent. That is, if it diverges to plus infinity or if it plus to minus infinity. Okay, so if un, a sequence un is always less than m, for n equal to 1, 2, 3, 4, it's always less than a certain number. But my sequence ekuti hapfuure as we practice number that you sequence a certain number m, any number that you can think of, and when m is a constant. If a sequence is always less than a certain number m, then we say that it is bounded above by m. Okay, then we say it is, like for example, that sequence that I showed you at the beginning, 1/2, 1/2, 1/3, that sequence is bounded. If all the terms in that sequence are less than 4, all the terms in this sequence are less than 5, all the sequence in that sequence are less than 10. So the sequence 1/n, which is 1/2, 1/4, 1 over 4, 1 over 5, 1 over 6, 1 over 6 is bounded above. And any number that you can think of, 4 is bounded above by 4, is bounded by 5, is bounded by 3, is bounded by 2. Okay, and it's called the upper bound. So 2 is the upper bound of that sequence. 3 is the upper bound of that sequence, is the upper bound. But we have got the smallest upper bound, which is the least upper bound, which is called the LUB. So in that sequence, 1 over n, which is 1, 1 is the least upper bound. Our first sequence here, tambotaurana here, 1 is the least upper bound. My upper bound akawanda. And it sequence here, you can 1 over n here. In a 1 half, 1/3, 1/4, 1/3. In my upper bound akawanda. 2 is the upper bound. 4, because all the terms are less than 2, all the terms are less than 5, all the terms are less than 100, all those are upper bound. But we have got the least upper bound, smallest upper bound, which is 1. 1 is the least upper bound. Okay. Then some terms are always bigger than a certain number. If un is always bigger than m, then the sequence is said to be bounded below. And m is called the lower bound. And my lower bounds are anekaka 1. So in that sequence, which is approaching 0, that is 1 over n, minus 2 is the lower bound, minus 6 is the lower bound, minus 10 is the lower bound, minus 100 is the lower bound. But we have got the largest lower bound, which is the greatest lower bound, which is 0. Remember, that sequence is approaching 0, and the first term is 1. So 0 is the greatest lower bound. Although minus 1 is the lower bound, minus 2 is the lower bound. So that sequence is said to be bounded. Saka tutaniswe mabounds, tutaniswe kuti haifi yakapfuura a certain number, haifi yakadarika a certain number, whether from above or from below. Then some sequences are bounded on both sides. If a sequence is between two numbers, m, a small letter m and a capital letter M, the sequence is said to be bounded. It's said to be, remember the previous is bounded above and bounded below. So this one is bounded below, and this one is said to be bounded above. Then when it's now just bounded, it means it has got two bounds, the upper bound and the lower bound, which is m and n, or the roof and the ceiling, which means the numbers in the sequence are between a small letter m and the upper letter and the capital letter M. They are always between that. Okay. So which indicate that un is always p for a convergent sequence. But the convergence is not necessarily true. Okay. If a sequence is such that, so you need to know the difference between a lower bound, an upper bound, and a bounded sequence. A bounded sequence is bounded on both sides, below and above. Okay. So if a sequence now is such that un plus 1 is always greater than or equal to un. Here we are talking of consecutive terms of our sequence, 10 and 11, 11 and 12. 13 and 14, and if a sequence is such that the bigger term, when you consider consecutive term, the bigger term is always bigger than the previous term. The sequence is said to be monotonic increasing, which means that the terms are always going up. 10 more pana 9, u9 more pana u8, u15 more pana u14. Okay, so if a sequence is such that it's said to be monotonic increasing. Okay, then if this monotonic increasing allows for equality, could maybe u14 and u15 is not gonna be equal, because we are saying un plus 1 is bigger than or equal to, so it's said to be monotonic increasing. But if it's strictly bigger than, could un plus 1 is strictly bigger than un, we say that the sequence is strictly increasing. It's monotonic increasing. Sometimes in monotonic increasing, we also have equality, equal terms, consecutive equal terms. Okay, but if it's strictly increasing, it's strictly bigger than, which means the previous term is always less than, not equal to. But if it's equal to, it's said to be monotonic increasing. Similarly, if you have got un plus 1 being less than un, our sequence is becoming smaller and smaller, the sequence is said to be monotonic increasing. In monotonic increasing, it allows for equality. Some consecutive terms can be equal sometimes. Okay, but if the next term is always smaller than the next term, we say it is monotonic decreasing. Then if the two consecutive terms are always smaller, the next term always being smaller than the previous term, we say it is strictly decreasing. it's very important to know these terms when we are looking at sequences. Consider this sequence: 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. You can see that this term, this sequence is bounded because these terms will never, it's bounded above and below. The terms will never go above, will never go below 1. Because my 1, 1, 1, I, they go up to infinity and they will never come to an end. The 1 billion terms in a 1, 1, 1, 1, 1, 1, 1, never 1 billion. And it. So that sequence now is always between 1 and 1, 2. This sequence, these terms will never end 1, and 1, 1 and 1, 2. Is it 1, 2? 1, 1. What is the next term which is next to 1, 1, 1, 1, 1, 1, 1, 1? Take around a 1, we get what? It's approaching what? This sequence is approaching what? It's approaching 1, 1, 2. It's approaching 1, 1, 2. It's approaching 1, 1, 1, 1. It's approaching 1, 2. Yes, it's approaching 1, 2. That's correct. It's approaching 1, 2. So such a sequence is bounded. It's bounded below by 1, and these terms will never go above 1, 2. So it is bounded, and it's not mono. That's why I highlighted this. It is strictly increasing sequence because the next term is always bigger than the previous term. So it is strictly. So in the notes I wrote monotonic, which is not correct. It is a strictly increasing term. The sequence 1 minus 1, 1 minus 1, 1 minus 1 is bounded as well. Okay, although it's not approaching any limit. Because this sequence with this pattern 1 minus 1, 1 minus 1, the numbers will never go above 1, and the numbers will never go below -1. So it's bounded above by 1, below by -1. And it is not monotonic. But in this case, it is an oscillating sequence. Okay. A new sequence is a sequence that converges to 0. If, like our first example, a sequence which converges to 0 is called a new sequence. Like we can have a sequence un, it's 1 over n minus 10 for n greater than 11. Okay. And then what else do we have? Limit of combination of sequence. Like from the theories of limits, Tambos Tower is. Tatikana ukanzaka limit as n approaches infinity of 2 minus 1 over n plus 3 over n squared. You can find these limits by looking at the limit of 2 minus the limit of 1 over n plus the limit of 3 over 2. If you are looking for the limit of this, you can look at the limit of the numerator over the limit of the denominator. But as long as the limit of the denominator is not 0. Okay, so that's how we find the limit of the combination of sequence. So to find the limit of this, we say limit of 2 minus limit of this minus limit of this. And limit of 2, the limit of a constant is that constant. As n approaches infinity, this approaches 2. The limit of 1 over n is 0. The limit of 3, 1 over n squared is also 0. So the limit of this whole thing is 0. The limit of this thing is, okay, when you're finding, let me show you this tricky. When you're finding the limit of a fraction, of a quotient of some functions, you divide each term by the highest power of n in that formula. So in this case, the highest power of n is n squared. So we divide each of these by n squared. So if I divide this one by n squared, I'll get 3 here. Divide this one by n squared, I get 5 over n. Divide this one by n squared, I get 5, or I get 5. Divide this one by n squared, I get 2 over n. Divide this one by n squared, I get 6 over n squared. So that's this one. So all the terms with the n on the denominator approaches 0. So this one approaches 0. This one approaches 0. This one approaches 0. So on the numerator, Tina 3. On the denominator, Tina 5. So the limit of this whole thing is 3 over 5. That's how we get the limits. And then we can also have a limit of this thing. From the properties of limits, when you are subtracting, you can find this separately. So I can have the limit of this minus the limit. But you can see, before we look at that, some functions need to be simplified. You can see that this thing is these are rational fraction. This is a rational term. What do we do if we rationalize this term? We rationalize this term by multiplying by its conjugate. Okay, so if I multiply by square root of, because with this square root it's become complicated. So the only way that I can be able to simplify is by more like multiplying by its conjugate. We know rationalizing the set forms under set forms. So I have to multiply by square root of n plus 1 plus square root of n. Both the numerator and the denominator. Remember, the denominator of this is over 1. So if I multiply this by this, this thing here becomes rational. Okay, then I've got 1 over this. Because I now have 1 over n. Anything that I've got over n approaches 0. So this whole thing approaches 0. That's the limit. Then next we want to look at the squeeze theorem. The squeeze theorem is very simple. It means just squeezing something. If you are squeezing something, it's between some certain two things, and we are simply saying under the squeeze theorem, we are simply saying if the limit of a sequence an is L, and a certain limit bn is also L, then if there exists an n such that we have another sequence that we know that is always, we have another sequence Cn, which is always less than an, but which is always bigger than an but less than an, or which is always between an and bn. Remember, to know zero limit here an as L. We also know the limit of bn as L. So what is the limit of Cl, of Cn? Cn is between an and bn. We know the smallest, we know the highest. So it means the limit of Cn is also L. Okay, that's the squeeze theorem. If the limit of an is L and the limit of bn is L, then the limit of Cn, which is between an and bn, is equal to L. Okay, we use this theorem to simplify limits of functions like cos n over n. Let's look at cos n over n. We know that from the graph of the cosine wave, we know that the cosine function is always between -1 and 1. Okay, so but we want to find the limit of cos n over n. So can we divide by n throughout this inequality? So we are starting with this inequality that we know. Okay, so divide by n throughout. We know that -1 over n is less than cos n over n, which is less than 1 over n. But the limit of -1 over n is known to be 0. And we know that when we are now finding the limit of this, we know that the limit of -1 over n is less than the limit of cos n over n using the inequality, is also less than the limit of 1 over n. But the limit of -1 over n we know is 0. Then the limit of 1 over n is also known to be 0. Therefore, the limit of cos n over n is also 0. So the limit of cos n over 0 is also 0. Because cos n over n is always between 1 over n, -1 over n and 1 over n. Okay, that's how we can apply the squeeze theorem. Okay, we use that to simplify quite a number of examples. You see, you come across other examples in the tutorial. So this is the end of this chapter 4 on sequences. Next, we are looking at series. That's the next chapter. Series now is an extension of sequences. Okay, my sequences are terms in terms of a sequence as they are. Now, when I talk about a series, we are now looking at the summation of terms in a sequence. A series is a summation of terms in a sequence. You can see here we are now adding plus. But when we were talking about sequences, A1, A2, A3, and my limits, the limits that we're talking about the limits of these terms of AN, not the limit of the sum. Okay, so generally under series, we'll be talking of sum of these series. Okay, so I'll end this lecture here. In our next lecture, we look at series. We are going to look at series. Okay, I hope you are following. Please do listen to this presentation in order so that you are able to follow, because in this module the concepts that are in earlier chapters are applied in the next chapters. So you need to make sure you understand the previous chapter before you go to the next chapter. So for you to go to this to series, understand sequences first. Thank you. We'll see you in the next lecture on finite series. Thank you.